In simple induction heating applications, as well as in wireless power transfer, the circuit shown is widely used. The circuit's power converter consists of two MOSFETs, the heating coil, L, the tuning capacitor, C, and two auxiliary coils, L1 and L2. The inductance of the auxiliary coils is set to be greater than that of the heating coil, so that the current in the heating coil is greater than the currents in L1 and L2. The heating coil, L, is actually the primary winding of a transformer, where the secondary is the workpiece. Therefore, the secondary winding is short-circuited and consists of a single turn. The workpiece is heated by eddy currents induced in it by the magnetic field generated by the coil. An additional cause of heating in ferromagnetic materials is hysteresis losses. The inductance of the heating coil and its series resistance depend both on the construction of the coil itself and on the characteristics of the workpiece. The power from the DC input source is equal to the AC output power is. The electrical efficiency of the circuit is. For high efficiency, the workpiece is placed inside the coil, and the air gap between them must be small. For low reactive power, the relationship must hold. The trigger circuit provides pulses to the gates of the two MOSFETs. The Zener diodes limit the voltage at the gate of each MOSFET. The main advantage of the circuit is its ability to self-oscillate at the resonant frequency. Although the circuit topology is simple, explaining how it works is quite complex. For this purpose, the converter was simulated in Matlab's Simulink. The component values in the model were selected based on the circuit shown in the figure. When the voltage across the resonant circuit is positive, MOSFET, S2, and diode, D2, are conducting. Thus, the gate voltage of MOSFET, S1, is very low, and it does not conduct. The switching from S2 and D2 to S1 and D1 occurs while the voltage in the resonant circuit is between plus and minus the supply voltage. When the voltage in the resonant circuit becomes negative and exceeds the supply voltage, S1 and D1 conduct. According to the simulation, the currents in the parallel resonance circuit are extremely high. As a result, capacitors with special specifications are required. Furthermore, the overall circuit assembly must take these very high currents into account. The converter is powered by a programmable power supply rated at 12 volts and a current limited to 10 amps. Initially, there is no workpiece inside the heating coil, so the current from the power supply is approximately 2.3 amps. The oscilloscope measures the voltage in the resonant circuit, which has a frequency of approximately 143 kHz and a peak-to-peak value of 66 volts. The multimeter measures the temperature of the heating coil. We use a transformer lamination as the workpiece. As the workpiece is inserted into the heating coil, the resonance frequency decreases, because the inductance of the coil increases. Furthermore, the current from the power supply increases significantly, because the equivalent resistance, R, increases. Within a few seconds, the lamination is fired. By modifying the coil design, the same power converter is used for wireless power transfer. The load is a 12-volt, 5-watt, automotive incandescent bulb. The oscilloscope measures the voltage and current at the load. As the two coils move closer together, the power delivered to the load increases. The efficiency of the circuit is very low, as the coil design is not optimal,